Number 1. The Indian Ocean Geoid Low. Look at a satellite gravity map of the planet, and your eye will eventually drift to a patch of ocean south of India. Something there looks wrong. The water itself appears to sag, as if a section of the sea has been pressed downward by an invisible hand. South of India and Sri Lanka, the ocean surface sits more than 100 meters below the level you would expect it to occupy. This is not a measurement error, and it is not a hole in the water. It is one of the strangest features on Earth's surface, and for decades it has puzzled the people who study the shape of our planet. This depression is called the Indian Ocean Geoid Low, or IOGL. It is one of Earth's strongest negative gravity anomalies, a place where the planet's pull is measurably weaker than the surrounding regions. To understand why that matters, you need to understand the geoid itself. The geoid is the theoretical shape the ocean surface would take if you removed every tide, every wave, every wind, every current, and every storm. Strip all of that away, and the sea would still not form a perfect sphere. It would bulge in some places, and dip in others, because the ocean follows the planet's uneven gravity field. Here's the part that surprises most people. A satellite passing overhead does not see the seabed directly. It cannot photograph the rock 4 kilometers down. What it sees is the height of the sea surface measured with extraordinary precision, and that surface height is sculpted by gravity. Where dense rock sits below, gravity pulls a little harder, and the water piles into a faint mound. Where the rock is light or the mantle is hot, gravity relaxes, and the surface settles into a shallow basin. The ocean, in effect, becomes a planetary gravity detector, spread across the entire globe, recording the structure of the Earth beneath it. The Indian Ocean Geoid Low is a dimple in that detector. It covers roughly 3 million square kilometers. Picture a gravitational hollow large enough to swallow much of a continent, and you start to grasp its scale. Scientists sometimes describe it as a gravity hole, though that phrase is a little misleading. Nothing is missing. The water is all there. The surface is simply lower than the average, because the gravity reaching up from deep inside the Earth at that spot is unusually weak. Ships first noticed something odd here in the 1940s when gravity surveys conducted from vessels picked up the anomaly, but ships can only sample one line at a time. It took satellite geodesy, decades later, to map the full shape of the low with proper spatial coverage and reveal just how vast it was. So, what causes it? The answer reaches back into deep geological time. After the supercontinent Gondwana broke apart, the Indian plate began a long northward drift toward Eurasia. Between the two land masses lay an ancient ocean called the Tethys. As India advanced, the floor of the Tethys was consumed, sinking down into the mantle through subduction. Those ancient oceanic slabs did not simply vanish. They descended deep into the earth, disturbing the mantle as they went, and may be connected to a vast structure beneath Africa known as the African Large Low Shear Velocity Province. The leading explanation involves density. Hot, low-density material rising in the mantle reduces the gravitational pull from below, while denser material around the edges tugs the geoid away from the central region. In 2023, researchers at the Indian Institute of Science built a computer model that traced the story back roughly 140 million years and suggested the modern form of the anomaly developed around 20 million years ago. Stand on a ship in that part of the Indian Ocean and you would notice nothing. No instrument on the deck, no view from an aircraft, no human eye would detect the depression. It is only visible from orbit through the patient mathematics of satellite mapping. The ocean surface is quietly recording the deep history of the mantle using nothing but gravity. And if a gravity map can expose a buried structure under 3 million square kilometers of water, the obvious question is what else it might be hiding. The next clue lies under something far more difficult to see through than water. Number 2, the Wilkes landmass anomaly. East Antarctica is a place where geology disappears. The seabed, the continental margin, the ancient rock, all of it vanishes beneath the East Antarctic ice sheet, a layer of ice so thick that ordinary mapping methods simply fail. Within that frozen continent sits a region called Wilkes Land, and beneath Wilkes Land, hidden under kilometers of ice, is one of the most debated anomalies NASA satellites have ever recorded. The discovery came from a pair of spacecraft called GRACE, short for the Gravity Recovery and Climate Experiment. GRACE worked through a clever trick. 2 satellites flew in formation, one chasing the other, and instruments measured the tiny changes in distance between them. When the lead satellite passed over a region of extra mass, gravity tugged it forward slightly, and the gap between the two spacecraft changed by a fraction of the width of a human hair. By tracking those minuscule shifts, Grace could map where mass was concentrated across the planet. Over Wilkes Land, Grace detected a strong mass concentration, a feature scientists call a mascon. The central anomaly measures roughly 320 kilometers wide, and around it, researchers proposed a broader circular structure, something close to 480 kilometers across. That circular shape is what made people stop and look closely. For comparison, the Chicxulub crater, the impact site linked to the extinction of the dinosaurs, is about 180 kilometers wide. A confirmed 480-kilometer impact basin would be extraordinary, far larger than anything in the standard catalog of Earth's craters. Researchers at Ohio State University proposed the impact interpretation in 2006. They connected the possible age of the structure to around 251 million years ago, placing it near the Permian-Triassic boundary. That boundary marks the Great Dying, the largest known mass extinction in Earth's history, an event that erased a vast share of all living species. Some speculation went further, suggesting an impactor up to about 30 miles wide could have been responsible. Here is where a careful researcher has to slow down. Grace is excellent at one job, locating where mass is concentrated. But it cannot, on its own, tell you why the mass is there. A gravity reading is not a diagnosis. To prove that a structure is an impact crater, geologists need physical evidence, the kind you can hold and examine. They look for shocked quartz, grains of mineral deformed by the immense pressure of an impact. They look for melt rock, for breccia, for the specific chemical signatures left when an asteroid strikes. Confirming any of that would almost certainly require drilling. And there are other explanations on the table. The mass concentration could be the result of a volcanic intrusion, a large body of dense igneous rock pushed into the crust. It could be related to mantle uplift or to the rifting that occurred as Gondwana broke apart and Antarctica's continental margin took shape. Each of these is a legitimate possibility. The ice cover that hides the structure also makes it nearly impossible to confirm any of them by direct geological work. So Wilkes Land remains genuinely unresolved. It is not a confirmed extinction-scale crater, and it would be irresponsible to call it one. But it is a real measurable anomaly, and the uncertainty is part of what makes it compelling. It shows how gravity measurements can point toward buried history long before geologists can ever touch it. The satellites have raised their hand and said something is here. They simply cannot yet say what. And while one Antarctic mystery sits frozen and possibly ancient, another lies beneath the same continent, and that one is very much alive. Number 3, the Marie Byrd Mantle Plume. It is tempting to think of West Antarctica as a vast, static block of ice, unchanging and inert. That picture is wrong. The ice there rests on top of active geology, and beneath one particular region, the planet appears to be feeding heat directly into the base of the ice sheet. The region is Marie Byrd Land, in West Antarctica. Beneath it, scientists have proposed the existence of a mantle plume, a deep source of geothermal heat rising from far below the crust. To understand why that matters for the ice above, you need to understand where the melting happens. Most people imagine ice sheets melting from the top down, warmed by sunlight and air. But a plume melts from the bottom up. This is called basal melting, melting at the very base of the ice sheet, at the boundary where ice meets rock. That basal meltwater does not just sit there. It collects, it flows, it forms a hidden plumbing system of subglacial rivers, channels, and lakes beneath the ice. And the water has a critical effect. A film of water at the bed reduces friction, and reduced friction lets the ice slide faster toward the ocean. This connects directly to the problem of ice sheet instability. To be clear, geothermal heat does not replace atmospheric and ocean warming as a driver of ice loss. It works alongside them, but heat from below can determine where the ice is most vulnerable to the warming from above. NASA's Jet Propulsion Laboratory studied this using a computer tool called the Ice Sheet System Model, or ISSM. The model simulates the full physical picture: melting, freezing, the transport of heat, the movement of water, and the friction at the base. A model alone is not enough, though. It needs real-world observations to keep it honest. Those came from systems like Seasat, a laser altimetry satellite, and Operation Icebridge, an airborne survey campaign that flew instruments over the ice to study the bed beneath it. The observations revealed something striking. Some subglacial lakes fill and drain over time, and as they do, the ice surface above them rises and falls by as much as 6 meters. The surface of Antarctica, in places, is gently breathing. To judge whether a plume is really present, scientists measure heat flux, the rate at which geothermal energy escapes upward through the crust. The unit is milliwatts per square meter. Across a normal non-volcanic part of the United States, heat flux runs around 40 to 60 milliwatts per square meter. Yellowstone, one of the most geothermally active places on the continent, averages roughly 200 milliwatts per square meter across the park. The modeling suggested that most of Antarctica's heat flux should stay below about 150 milliwatts per square meter, but one inland region near the Ross Sea appeared to require something higher, in the range of 150 to 180. That elevated value is part of the evidence pointing to a plume. The plume itself is ancient. Estimates place its age between 50 and 110 million years, which means it long predates the modern West Antarctic ice sheet. The heat source was already there, waiting before the ice ever arrived. What we see today is two forces working together: heat rising from below and warming pressing from above. Ice sheets, after all, obey the same fundamental laws of heat, pressure, and friction as the rest of the planet. And those same laws govern a structure on the other side of the world, one that grew so large it briefly held a world record before scientists had to rewrite their own conclusion. Number 4. The Tamu Massif. Travel east of Japan into the northwest Pacific and you pass over a broad submarine highland called the Shatsky Rise. Hidden within it is a structure that ranks among the largest volcanic features ever identified on Earth, and yet for a long time nobody recognized it for what it was. The structure is called Tamu Massif. Tamu Massif is an enormous volcanic mountain, entirely submerged. Its summit lies roughly 2 kilometers below the surface of the ocean. Its base reaches down to about 6.4 kilometers depth. It sits approximately 1,600 kilometers east of Japan. And here's the reason it stayed hidden in plain sight. It is broad and low. A classic volcano has a recognizable peak, a cone you can point to. Tamu Massif spreads out so widely and rises so gently that, even with data in hand, it did not look like a single volcano at all. In 2013, a research team made a dramatic claim. Tamu Massif, they argued, might be the largest single shield volcano on Earth. The reported area was about 120,000 square miles, a footprint comparable to the state of New Mexico. To grasp how startling that was, compare it to Mauna Loa in Hawaii, long considered one of the largest volcanoes on the planet. Tamu Massif appeared to dwarf it. The claim genuinely shocked the scientific community. The evidence behind it was substantial. Drilling recovered core samples containing thick basaltic lava flows, the dense dark rock produced by large volcanic eruptions. Seismic reflection profiles, which use sound waves to image the structure beneath the seabed, suggested lava flows that radiated outward from a central summit. The gentle slopes fit the profile of a shield volcano, the type built by fluid lava spreading far before it cools. The structure was dated to roughly 145 million years old, and it appears to have gone quiet within just a few million years of forming. But science does not stop at the first dramatic headline. In 2019, a new analysis looked at the magnetic evidence, and it changed the story. Rocks record the Earth's magnetic field as they cool, and the seabed around Tamu Massif showed linear magnetic stripes. Those stripes are the signature of crust formed at a spreading ridge, where two plates pull apart and new seafloor is generated in parallel bands. That pattern is hard to reconcile with a single central shield volcano. The reinterpretation suggested Tamu Massif was shaped, at least in part, by ridge-related processes rather than one giant volcanic vent. So the label changed. The clean phrase, largest single shield volcano on Earth, became much weaker. But notice what did not change. Tamu Massif is still one of the largest volcanic mountains on the planet. The payoff survived even as the explanation was revised. This is how science actually works. A first answer is offered, new evidence arrives, and the conclusion is corrected without the discovery losing its significance. Volcanic scale, in the end, is written in basalt, in gravity, in magnetism, and in time. And the next discovery is also written in broken rock on a seabed that looks as though it was physically torn apart. Number 5. The Banda Detachment Fault. In eastern Indonesia lies the Banda Sea, a body of water sitting inside one of the most tectonically complex zones on Earth. Plates collide, slide, and pull apart here in a tangle that has challenged geologists for generations. And within that tangle is a feature that makes the seafloor look as if it has been unzipped, the Banda Detachment Fault. The fault sits near the Weber Deep, an extraordinarily deep basin. The Weber Deep reaches about 7 kilometers below sea level, one of the deepest points in the world that is not part of an ocean trench. The Banda Detachment itself is one of the largest exposed fault plains ever identified on Earth. The exposed fault surface covers roughly 60,000 square kilometers. To put that in everyday terms, the bared face of this single fault is about the size of a small country. To understand what you are looking at, you need to know what a detachment fault is. Most people picture a fault as a steep crack, 2 blocks of rock grinding past each other along a near vertical line. A detachment fault is different. It is a low-angle fault, a fault that slopes gently, and it accommodates an enormous amount of displacement. As a region is pulled apart by extension, the crust stretches and thins. In the Banda region, that extension was dramatic. The crust experienced roughly 120 kilometers of horizontal stretching. As it pulled apart, the deep basin formed, and the crust was unroofed, meaning its overlying layers were dragged away to expose what lay beneath. Rocks from deep in the crust, and even from levels close to the mantle, can be brought up toward the surface by this process. The evidence is written across the seabed itself. The fault surface is marked by hundreds of straight, parallel scars. These lineations are the physical record of tearing, sliding, and progressive extension etched into the rock as the crust was pulled apart over time. It is important to be precise here. The Banda Detachment is not a narrow crack. It is a broad geological surface, a vast exposed plain, and that is exactly what makes it scientifically remarkable. A note of caution belongs here too. It would be easy to dramatize this by saying the seabed dropped 7 kilometers in one violent motion. That is not what happened. The deep basin and the exposed fault are the product of extension accumulated over a long span of geological time, not a single instantaneous slip. The accurate picture is more interesting than the exaggeration, a slow, immense unzipping of the Earth's crust. This matters beyond pure geology. The Banda region lies within the Pacific Ring of Fire, the belt of intense seismic and volcanic activity that rims the Pacific. Large faults store and release tectonic stress, which makes the region significant for understanding earthquake and tsunami hazard. Mapping the Banda Detachment relied on satellite altimetry to interpret regional gravity and bathymetry, but direct high-resolution seafloor mapping and field analysis were also essential to confirm what the satellites suggested. The seabed here preserves deformation as geometry, as stress, and as broken rock. And if a fault the size of a country can hide beneath the waves, the next discovery asks an even larger question. How many entire mountains have we simply failed to count? Number 6. SWOT and the hidden Seamount explosion. Here's a fact that should genuinely unsettle you. The ocean floor, the solid terrain of our own planet, is still largely unmapped. Earth hides mountains under ordinary-looking stretches of water. And we are only now learning how many. In 2023, a satellite-based update added 19,325 newly mapped seamounts to the global catalog. A seamount is an underwater mountain, typically a volcano, rising from the seabed. Before this update, the catalog contained about 24,643 features. In a single revision, the known count of these mountains nearly doubled. It is worth being precise about where that number came from. The 19,325 figure was derived mainly from data collected by 2 satellites, Cryosat-2 and Sera El Altikar, both radar altimetry missions. That distinction matters because there is a newer mission that often gets the credit, and its real importance lies in the future. The mission is SWOT, the Surface Water and Ocean Topography Satellite, a joint project between NASA and the French space agency CNES. SWOT launched in December of 2022. It measures the height of the sea surface with centimeter-level precision, and it covers roughly 90% of the globe every 21 days. The physics SWOT relies on is the same principle that runs through this entire story. A seamount is a large mass of dense rock. Its gravity pulls the surrounding water toward it, and the sea surface rises into a tiny bump directly above the mountain. The bump is small, often just a fraction of a meter over a mountain that is kilometers tall, but it is measurable from orbit. Map the bumps, and you map the mountains. What sets SWOT apart is an instrument called CARIN, the K-band radar interferometer. Older altimeters measured the sea along a single narrow line directly beneath the satellite. CARIN measures a wide swath, a broad strip of ocean on each pass. That wide swath approach captures far more spatial detail than the older single-track method. Here's the practical consequence. Older satellites could reliably detect seamounts taller than about 1 kilometer. SWOT may be able to detect features less than half that height. The numbers tell the story of the learning curve. The known count of seamounts taller than 1 kilometer stands at roughly 44,000. Improved mapping, drawing on missions like SWOT, could push the known total toward 100,000. And beyond seamounts lie abyssal hills, smaller features that are only now becoming visible. Abyssal hills may cover something like 70% of the seafloor, making them one of the most common landforms on the planet and one of the least mapped. This is not merely a counting exercise. Seamounts shape the ocean. They steer currents and tides, they influence the movement of nutrients, and they create biological hotspots where life concentrates. Every newly mapped mountain refines our understanding of how the ocean actually works. Ocean topography, read from the height of the surface, turns hidden mountains into measurable gravity signatures. And the next discovery shows that the seabed records not just shapes, but rhythms, pulses of the Earth itself frozen into rock. Number 7. The Reykjanes V-shaped ridges. Southwest of Iceland, the Mid-Atlantic Ridge runs through the cold North Atlantic. Along one stretch, the Reykjanes Ridge, the seafloor carries a pattern so regular it looks almost designed. Read correctly, it is a geological recording, a waveform pressed into the ocean crust. The Reykjanes Ridge is part of the Mid-Atlantic Ridge, the immense spreading system where the North American and Eurasian plates pull apart and new seafloor is born. What makes this section special is its neighbor. The ridge lies close to the Iceland Mantle plume, the deep upwelling of a hot material that built Iceland itself, and the seafloor along the ridge is marked by a series of V-shaped ridges and troughs, chevron patterns pointing along the spreading axis. You would never see these patterns from the deck of a ship. Individual ship tracks sample only narrow lines, and the chevrons are too large to recognize from isolated passes. It took satellite-derived gravity and bathymetry to reveal the V-shapes at the scale of the whole basin, straddling the spreading ridge axis on both sides. So what do they record? The answer is crustal thickness, and it changes over time. When the supply of magma from the mantle increases, thicker crust is produced. When the melt supply weakens, thinner crust forms. The V-shaped ridges are alternating bands of thicker and thinner crust, and that alternation points to a pulsing flow from the Iceland plume. The plume does not deliver heat at a perfectly steady rate. It pulses, and those pulses move outward from Iceland beneath the lithosphere, the rigid outer shell of the Earth, like slow waves spreading from a source. The timing of these pulses is measured in millions of years. The intervals run on the order of several million years, and the working range used for the mantle wave timing is roughly 5 to 10 million years between pulses. The speed at which the plume material flows affects the angle of the V-shaped ridges, the sharpness of the chevrons. The rate at which the ridge spreads then stretches those patterns across the seafloor, like a recording played back at different speeds. The pulsing plume idea is associated with a model published by the researcher Ito in 2001, describing radial plume flow that pulses outward. But, in keeping with how this story works, it is not the only explanation. The V-shaped patterns might instead reflect ridge jumps, where the spreading axis relocates over time. They might reflect propagating rifts or variations in buoyant mantle that have nothing to do with regular pulses. To test the competing models, scientists turned to direct evidence. International Ocean Discovery Program Expedition 395 drilled into the crust along the Reykjanes Ridge specifically to gather the rock samples needed to distinguish between the hypotheses. The ocean crust, it turns out, can record the rhythm of the mantle written through heat, melt, and the steady motion of plates. But none of these discoveries would have been possible without a single short-lived mission that proved the whole idea could work. To understand all 8, you have to go back to where it started. Number 8. Seasat, the 100 days that mapped the seafloor from space. The year is 1978. NASA launches a satellite called Seasat, an ocean-observing spacecraft, in June of that year. It was managed by NASA's Jet Propulsion Laboratory, and it carried a distinction that makes it the foundation of this entire story. It was the first satellite designed specifically for ocean remote sensing. Seasat was an ambitious machine. It carried a suite of instruments: a radar altimeter, a synthetic aperture radar, a scatterometer, a radiometer, and microwave sensors. Each had a job, but the instrument that mattered most for the future of seafloor mapping was the radar altimeter. The altimeter measured one thing with precision: the distance from the spacecraft down to the ocean's surface. It did this by timing a radar pulse traveling at the speed of light from the satellite to the sea and back. A raw distance measurement is not yet useful, though. To turn it into something meaningful, scientists had to apply corrections, accounting for the satellite's exact orbit, for delays caused by the atmosphere, for the height of waves, and for the choice of a reference ellipsoid, the idealized mathematical shape of the Earth. Once corrected, that distance became sea surface height, and sea surface height reveals ocean topography, the subtle hills and valleys of the sea. Seasat did not last long. It operated for 105 days, and its mission ended on October 10th, 1978. NASA's listed cause was a short circuit in the electrical power system. In that brief window, it collected roughly 70 days of oceanographic data. But the volume was remarkable. More than 50 million individual physical measurements fed the first global maps of their kind, and those maps revealed the principle that underlies every discovery in this script. Ridges, trenches, seamounts, and contrast in rock density all affect gravity. Gravity, in turn, creates tiny bulges and depressions in the ocean's surface. Seasat proved that a satellite measuring the height of the water could indirectly sense the shape of the seabed. At least one previously unknown major feature appeared in Seasat imagery, a tangible demonstration that the method worked. Over the years, declassification rumors have attached themselves to the Seasat story, suggestions that its early shutdown was tied to military secrecy. These are best treated as rumors rather than established mission history. The documented cause remains the power system failure. What is not in doubt is the lineage. Seasat led directly to later radar altimetry missions, to the gravity work done by Grace-style satellites, and eventually to SWOT. Modern ocean mapping began the moment spaceflight learned to measure millimeters of water. 8 discoveries down, the individual stories are told. But the more interesting question is how a satellite hundreds of kilometers up can map a seabed it never actually sees. Now that we have walked through all 8 discoveries, it is worth pausing to examine the shared technique behind them, because the method is as remarkable as any single finding. Start with a fact that sounds simple, but is easy to forget. The ocean's surface is not a perfect sphere. It has shape. Scientists describe that shape using sea surface height, which is measured relative to a mathematical reference surface, an idealized model of the Earth. They also use the geoid, defined as a gravity-controlled equipotential surface, the shape the sea would take under gravity alone. The link between the seabed and the surface is gravity. A dense seafloor feature, like a seamount, slightly increases the local gravitational attraction. That extra pull draws water toward it, piling the sea into a low mound directly above the mountain. The reverse also happens. A region of low-density mantle or crust depresses the geoid, creating a hollow exactly as it does in the Indian Ocean Geoid Low. Radar altimetry is the tool that reads this. The technique works by timing a radar pulse sent from the satellite to the ocean and back. Because radar travels at the speed of light, that timing gives a precise satellite-to-sea distance. Then, precise knowledge of the satellite's orbit converts that distance into sea surface height. As with Seasat, the measurement only becomes trustworthy after corrections for tides, waves, atmospheric delay, sea state, and instrument drift. And because any single pass contains noise, satellites make repeated global passes, averaging many measurements to sharpen the signal. Different missions add different strengths. Grace-style gravity measurement worked not by altimetry but by tracking the changing distance between two twin satellites, sensing mass directly. SWOT differs again, measuring wide swaths of ocean instead of only narrow ground tracks, capturing two-dimensional detail. Ship sonar, by contrast, gives direct bathymetry, an actual measurement of depth, but a ship can only cover the limited route it sails. Much of the ocean remains unmapped at high resolution by ships simply because no vessel has ever passed over it. This is why satellite maps and ship maps complement each other. Satellite maps are lower in resolution but globally consistent, covering everything. Ship surveys are precise but local. In practice, altimetry guides ship expeditions, pointing them toward suspicious features worth investigating in detail. The one limit to keep in mind is this: satellite gravity can suggest the shape of a structure, but it cannot confirm what kind of rock it is made of. Spaceborne ocean mapping is indirect, mathematical, and, despite that indirectness, extraordinarily powerful. That limitation deserves a closer look, because it is the difference between a discovery and an explanation. Satellites are excellent at finding anomalies. An anomaly in this context is simply a measurement that differs from the expected background, a reading that stands out. But finding an anomaly is not the same as understanding it. A gravity anomaly does not automatically identify an impact crater. It identifies a place where gravity is unusual and nothing more. Wilkes Land is the clearest cautionary example. The mass detected there is real. But that concentration of mass could come from impact melt, from dense igneous rock, or from a particular arrangement of crustal structure. Each is consistent with the gravity data. Diagnostic proof of an impact requires physical samples and specific mineral evidence, the shocked quartz and melt rock that only drilling could recover. Until that evidence exists, the honest description is an anomaly, not a crater. Tamu Massif is the case where the first headline changed. The 2013 claim of the largest single shield volcano was a reasonable interpretation of the data available at the time. Then, the magnetic stripes were studied, and that evidence undermined the shield volcano picture. Far from being an embarrassment, this is a sign of strength. Science becomes more reliable, not less, when claims are revised in the face of better evidence. The Seamount figure offers a lesson in precision. The number 19,325 came from a 2023 satellite catalog update, drawing mainly on Cryosat-2 and Soral-Altic, not specifically from SWOT's first year of operation. SWOT's real importance lies in improved future detection. Getting that attribution right matters because careless phrasing creates false history. It helps to keep four things mentally separate. Bathymetry is the depth of the seabed. Gravity is the pull of mass. Geoid height is the shape of the equipotential surface. And geological origin is the actual story of how a feature formed. A single map can support several competing hypotheses about that origin. Confirmation comes only from additional methods: ship surveys, seismic profiles, drilling, and geochemistry. Uncertainty, then, is not a weakness of satellite mapping. It is a feature of it. The satellites reveal anomalies before scientists know their cause, and sensational phrasing must not be allowed to outrun the evidence. A well-made documentary can preserve genuine wonder while staying accurate, and it can give the audience permission to enjoy a mystery that is not yet solved. The seabed is not just hidden, it is interpreted layer by careful layer. Several of these discoveries, looked at closely, are not really about the seabed at all. They are about the machine beneath it. Think of the seabed as the top surface of a far deeper system, the Indian Ocean. Geoid Low is the Mantle scale example. Ancient slabs of oceanic crust can sink hundreds, even thousands of kilometers down into the Earth. That sinking process is subduction, where one oceanic plate dives beneath another. The slabs of the old Tethys Ocean, connected to India's long northward journey, descended into the mantle and altered its density distribution, and those density differences are what reach up to shape gravity at the surface. Marie Byrd Land is the heat example. A mantle plume is buoyant hot material rising from depth, and its heat can weaken the crust above and melt ice from below. Reykjanes shows plume-ridge interaction directly. Ridges create new crust as plates separate, and when mantle pulses increase magma production, the crust grows thicker. Crustal thickness becomes a measurable record of how much melt the mantle supplied. Tamu Massif is the large igneous product example. Basalt is the rock that records large volume melting events, and the Shatsky rise provides the broader context of a volcanic plateau. Banda connects to tectonic stretching and the thinning of the lithosphere, where low-angle detachment faults expose deep crustal levels that are normally buried far out of reach. Every one of these examples ties back to the same four agents: heat, density, pressure, and buoyancy. Read in this light, seabed maps become something larger. They become maps of the Earth's internal engine, the slow circulation that drives the surface world. Antarctica earns a special place in this story because it appears on the list twice, and for two completely different reasons. Antarctica is the hardest continent on Earth to read geologically. Ice hides everything: the bedrock, the basins, the faults, the heat flow, and distant, and any impact candidates that might be buried below. Wilkes Land is the buried mass mystery, a possible ancient structure frozen in place, and if it is an impact crater, long inactive. Marie Byrd Land is the active heat mystery, a present-day source of geothermal energy shaping how the ice behaves right now. One is a question about the deep past. The other is a question about the present. Because ice thickness prevents ordinary geological mapping, scientists rely on indirect methods, and it is worth noting the evolutionary steps in their toolkit. Airborne radar detects the shape of the bed beneath the ice. Gravity satellites detect buried mass. Laser altimetry measures changes in the ice surface itself. Each method peels back the ice in a different way. The stakes are real. Much of Antarctica's bed lies partly below sea level, which makes those ice sheets marine-based. And marine-based ice can become unstable when its grounding line, the boundary where ice begins to float, retreats. Basal melt, the melting at the ice bed boundary, and geothermal flux, the heat escaping from the interior, both feed into this. Subglacial water can lubricate the flow of ice toward the sea. It is important to separate two kinds of forcing. A hidden crater, if it were ever confirmed, would be ancient and inactive, geologically interesting, but not a driver of today's changes. A plume or heat anomaly, by contrast, can influence present-day ice dynamics. And neither replaces the central fact that climate warming remains the primary force behind current ice loss. What bedrock heat does is help determine where the ice is most vulnerable. Antarctica proves that a seafloor, in the broad sense, can be hidden under ice, and not only underwater, and that mapping such a place demands indirect signals at every step. These discoveries also matter for reasons that have nothing to do with spectacle, because hidden seabed structures carry real human stakes. The Banda Detachment introduces hazard. Faults store and release tectonic stress. And the Banda region's position in a complicated plate boundary zone makes it relevant to earthquake and tsunami risk. Steep seafloor relief adds another danger: the risk of submarine landslides, which can themselves generate tsunamis. Seamounts pose hazards too. An uncharted seamount can endanger a submarine or a deep-diving vehicle. Better maps have practical value. They improve route planning for undersea cables, and that matters more than most people realize because the great majority of international internet traffic depends on submarine cable networks running across the ocean floor. Seamounts also shape life. By steering currents upward, they create biological hotspots. That upward motion, called upwelling, delivers nutrients from the deep to sunlit waters where life can use them. Abyssal hills and general seafloor roughness affect deep ocean mixing, and that mixing influences how heat and carbon move through the ocean, which connects directly to climate. Even the Indian Ocean Geoid Low has applications. Geoid models matter for satellite navigation and for the Earth reference models that underpin precise positioning, and they are essential for accurately measuring sea level. Tamu Massif feeds into the study of large igneous provinces, and large volcanic provinces can affect ocean chemistry and ecosystems. The Reykjanes ridges inform our understanding of mantle temperature and the rate of crust production, and Antarctic basal heat directly affects projections of future sea level rise. Mapping the seabed, in short, improves both pure science and practical risk planning. The hidden ocean floor touches climate, infrastructure, biology, and human safety. To see how all of this came together, it helps to lay the technology out as a timeline, because the progression has a clear shape. It begins with Seasat in 1978, the proof of concept. 105 days was a short life for a spacecraft, but it was scientifically transformative. Seasat gathered about 70 days of oceanographic data, and its radar altimeter proved that the ocean surface could reveal the seabed below. From there, later radar altimetry missions expanded global ocean coverage, and repeated orbital tracks steadily improved resolution and confidence. Then came GRACE, a mass measuring system that worked by sensing gravity directly, and GRACE helped reveal large-scale anomalies like the one under Wilkes Land. ICESat brought laser altimetry focused on the elevation of ice. Operation Icebridge filled gaps with aircraft-based observations, bridging between satellite missions and connecting directly to studies of Antarctica's bed and ice sheet behavior. GRACE-FO followed, providing continuity for monitoring the Earth's gravity field. Cryosat-2 and SORAL Alti-Ka contributed high-resolution altimetry, and it was their data that drove the expansion of the catalog by 19,325 seamounts. Finally came SWOT, the modern wide swath leap covering most of the globe every 21 days. Its CORIN instrument delivers two-dimensional swath data rather than the single-track profiles of older satellites. Each mission, in its turn, removed one specific kind of blindness. And through all of it, ship sonar still matters because direct measurement remains the standard for final confirmation. Every new satellite turned the ocean from blank space into measurable terrain. That leaves one last question worth sitting with. The same maps can support competing explanations, so it is worth comparing three broad ways of interpreting everything you have heard. The first interpretation is mainstream geophysics. This view explains most features through plate tectonics and mantle dynamics, the well-tested machinery of modern Earth science. Under this view, the Indian Ocean Geoid Low reflects density differences in the mantle. Wilkes Land remains a gravity anomaly until physical samples prove an impact origin. Marie Byrd Land reflects geothermal heat influencing basal melt beneath the ice. Tamu Massif becomes a huge volcanic construction shaped by ridge-related processes. The Banda Detachment reflects extreme crustal extension and low-angle faulting. The Reykjanes V ridges reflect Plume ridge interaction and a changing magma supply. This interpretation is the one best supported by the current evidence, and it accounts for the features without requiring anything exotic. The second interpretation is historical and geological reconstruction. This view places its emphasis on lost ocean basins and ancient plate events. It foregrounds the Tethys Ocean, the breakup of Gondwana, the formation of the Shotski Rise, and the rifting of Antarctica. It treats each discovery as a surviving trace of a vanished tectonic world, a fragment of a planet that no longer exists in the same form. It asks how much of Earth's deep history is preserved, hidden, underwater, or under ice. This perspective gives the whole subject a deep time framework, a timeline that runs from the Great Dying 251 million years ago all the way to the satellite age. It is less a rival to mainstream geophysics than a way of organizing the same facts around the theme of lost worlds. The third interpretation is speculative, and it should be handled with clear boundaries. Speculative interpretation explores unresolved possibilities without calling them facts. It can ask whether Wilkes Land truly hides a Permian-scale impact structure. It can ask whether mantle pulses behave like long-period planetary rhythms, almost like a slow heartbeat of the Earth. It can ask whether many more megastructures remain entirely invisible in the poorly mapped stretches of the ocean. These are legitimate questions, and curiosity about them is healthy. The discipline lies in repeating each time what evidence would be needed to move a speculation into the realm of established fact. Curiosity and proof are not the same thing, and keeping them separate is what makes the curiosity worthwhile rather than misleading. What ties all three interpretations together is a single realization. When NASA mapped the seabed, it did not simply chart water. It exposed hidden structure, the buried architecture of a planet we have still not fully seen. 8 discoveries, from a gravitational dimple south of India to a 100-day mission in 1978, all rest on the same foundation. Gravity, heat, density, pressure, and motion are the fundamental laws shaping a world that, even now, with satellites circling overhead every 21 days, continues to keep most of its surface a mystery.